the University of Moscow. In Pakistan, he has been recognized with the Sitara Imtiaz. He's a fellow of the Pakistan Academy of Sciences and has been associated with the Pakistan Physical Society as well. It's an honor always to hear you speak. Thank you very much for being here. Please take it from here.
Thank you. Thank you very much. So when you invited me, so you said what I should talk about, and whether it should be a research talk or whether it should be a popular talk. So then I think we had come to the conclusion it should be more an introductory talk, and a smaller part would be covered by the research part.
Absolutely.
So knowing that you don't teach plasma physics over here, so I thought first few sort of slides or minutes, we'll just introduce a plasma. Then this work that has recently, I think it appeared this year, earlier on this year, in Chaos, Solitons, and Fractals. So it's quite a long paper if you look at it, because we've tried to cover quite a few things. And so I would talk a little bit about quantum plasmas. Then what are the type of methods that we are using? We are eventually do a nonlinear dynamical analysis. So some few words about that. And then we look at a special type of
Did it get stuck?
Okay. So, so the first 3 points are more the introductory part. And then, depending on how much time I have, then we'll see the specific problem that we have looked at. So I had come here last year also, and we talked about plasma physics at that time also. So, but I still want to go through some very sort of working definitions of a plasma. And so a plasma is an electrically conducting medium in which there are roughly equal numbers of positively and negatively charged particles. And it is produced when the atoms in a gas become ionized. So, if you heat a solid, it becomes a liquid. If you heat a liquid, it becomes a gas. When you give it further energy, the atoms are stripped of their electrons. So the electrons and the positively charged nuclei they coexist, but electrons are no longer bound. So it's a kind of a soup which exists. So it becomes an electrically conducting medium. And neutrality is maintained. Usko hum quasi-neutrality bhi kehte hain, because locally there can be sort of fluctuations. तो उससे कोई ना कोई charge imbalance create होता है, but overall, if you look at the system, it is neutral. So पुराने ज़माने में इसको, when plasmas became fashionable about 60, 70 years ago, it began to be referred to as the fourth state of matter, as opposed to the 3 states of more familiar ones, solid, liquid, and gaseous. So plasma physics got a lot of impetus for 2 reasons. One, because after the explosion of the hydrogen bomb, people decided that this energy could be used in a positive manner. The idea was to try to contain a plasma, because this is a fusion reaction which takes place, and from basically hydrogen ke jo isotopes like deuterium and tritium. So there has been a great effort in this direction since the early 50s. The Russians decided to popularize this research. Unka ek bahut famous experimentalist tha, Artsimovich, who went to London at a conference, and there he opened up what was earlier a closed sort of a thing, and people wouldn't talk about this research. So he, as a matter of policy, it wasn't कि वो कोई dissident था, but he there decided that this would become open research. So तब से plasma physics has been mostly a very open field of research where you see a lot of collaboration. So a lot of money started flowing into plasma physics. कि इसमें से fusion निकलेगी, that would be the ultimate source of energy, which was relatively clean because the radioactivity part is very small in a fusion machine. Then in the late 50s, we had the first satellite which went up. And it was the Soviets, the Russians who led this effort. First man in space came up, Yuri Gagarin. And so again, that became now another possibility. These satellites which go up, they could carry a scientific payload. They could explore the medium in which they were going to be located. And that medium was a plasma medium. So now we know that 99.9% of the matter in the observable universe is in the plasma state. We live in that little 0.1% where naturally occurring plasmas come. Of course, if you take into account, so we are talking about observable universe. The dark energy and dark matter, which nobody sees, but it's presumed to be there, that of course is not part of this. So these two directions came in. So if you sort of, this is a schematic sort of a diagram, the red dots are the positively charged heavier parts, ions, and the small dots are the electrons. So due to, now all the time Coulomb forces are acting between the particles. So कहीं भी अगर छोटी सी एक disturbance होगी, so then the ions would stay put because they are heavier and the electrons would get attracted towards the ions. And then they overshoot their position, then again they feel an attraction, they come back. So the whole plasma starts participating into it, into this thing, and a natural oscillation is set up, which is the expression given at the bottom, which is called the plasma frequency. So you will never find a plasma which is absolutely static. It is always sort of oscillating, moving. And the word plasma comes from the Greek, as most of our other scientific terminology, which also comes from the Greek. So it means jelly-like. So जैसे आपके पास jelly है, आप उसको prod it with a finger at one point, so the whole jelly starts shaking. So that is where the word plasma has come from. So that is why what plays a very important role over here is the collective behavior. Now, इसको study करने के लिए people started looking at it about 100 years ago, even more. And in gas discharges and all, Langmuir was a big name. जिसने ये सारा, we have this concept of a plasma frequency. इसको Langmuir frequency भी कहा जाता है, where it was observed. और फिर things moved on. So theoretical methods also developed. So plasma physics borrowed heavily from fluid mechanics because of its collective behavior. It behaved like a fluid, but it was a charged fluid. उसमें एक electron fluid है, एक ion fluid है, या अगर कोई और charged species है तो वो भी शामिल है, but overall maintaining quasi-neutrality. So the Navier-Stokes equation, which is the Newton's law of motion for a fluid, that became generalized for plasma physics. And the force terms got replaced by the electromagnetic forces. And mostly we considered plasma to be collisionless, because if collisions बहुत ज़्यादा होंगी तो long-range interactions would get neglected, and the plasma would start behaving like an ordinary fluid. So as time went on, हमारी observations भी बढ़ती चली गई, and then when people started looking at these stars, like neutron stars and all, तो उनकी density बहुत ज़्यादा थी of the and then we could talk about a degenerate or a quantum plasma. So that is what this work in this paper is all about. We are looking at degenerate plasmas. So I'm sure you're familiar with all this, that we can measure quantum effects by the de Broglie wavelength. And this represents the spatial extension of particles due to uncertainty. For classical regimes, this is so small that particles can be point-length, by which I mean that if particles अगर दूर-दूर हैं, तो उनके साथ जो associated matter waves हैं, वो दूर है. But as the matter becomes more dense, you have an overlap of these, the wave-like structure associated with a body. So lighter particles will have a large, because mass occurs in the denominator, they'll have a large de Broglie wavelength, and they're going to be interacting with each other. So density ke saath, a matter which is classical can become quantum-like, uska behavior aata. So we put in some elements of quantum theory into our calculations because we say that this is now degenerate matter. And another way of looking at this is that you define something called a Fermi temperature. This is a familiar expression for Fermi energy.
Excuse me, can we not use this as a pointer? Because I just realized it's reflecting crazy and it might get into somebody's eyes.
Okay. So anyway, the red box shows, अगर आप left-hand side को 1 minute के लिए ना देखें, that is the expression for the Fermi energy, which is entirely dependent on the number density. बाकी सारी चीजें constant है for a given mass of particles.
Yeah.
So Fermi energy electrons के लिए ज़्यादा होगी, heavier particles के लिए कम होगी. So if you have energy, you can formally look at it in terms of temperature. So we define Boltzmann constant time TF, which is called the Fermi temperature. It is not a temperature that you can measure with a thermometer like an ordinary temperature की हम बात करते हैं. But there is this concept of Fermi temperature. So quantum effects are important when the Fermi temperature is much larger than the normal ambient temperature of a medium or whatever. So if this is so, which is what we see when we look at the numbers, the high densities which are present in astrophysical objects, so the Fermi is much larger, the Fermi temperature, than the ordinary temperature, whatever is estimated from observations. So then it means that quantum effects are important. So so somehow we have to build this into our model. And so when we write down equations of motion or the Navier-Stokes equation, we have to take some quantum effects into account. For example, instead of looking at the thermal velocity, we'll look at the Fermi velocity. Or instead of looking at Maxwellian distributions, which are typical for classical plasmas, we will look in terms of Fermi-Dirac distributions. If the Fermi temperature is much, much larger than the ambient temperature, then we can approximate it to be equal to 0. Then we'll say that this is a fully degenerate plasma, although it might in real terms be millions of degrees, but the other temperature is much higher. So things are, on a relative scale. So then we have a fully degenerate plasma, and the Fermi-Dirac distribution function reduces to a Heaviside distribution, which is much easier to deal with. But in what we have done, we have continued, we've retained the temperature term. It's a small term, it's a correction term, but this we say that these are partially degenerate plasma. Okay. So let me sort of stop the plasma introduction and let's look at a few other things. And I'm sure you are familiar with this phase space, yes, state space. Just look at it. If you look at a simple harmonic oscillator, you can break it up into two equations, the box at the bottom over here. So the simple harmonic oscillator, this is in dimensionless form. This can be written as a set of two first-order equations. So such equations are called autonomous equations because time doesn't appear explicitly on the right-hand side. So हम phase space की बात करते हैं, which is a mathematical construct के instead of plotting x versus t or v versus t time, we plot, let's say, v versus x, x dot versus x. So we see the motion of a particle for a simple harmonic oscillator. It goes round in a circle. तो यहाँ पर एक related concept ये भी है कि we use when we do nonlinear dynamical analysis, we use what is called the Poincaré sections. Are you familiar with Poincaré sections? अगर एक आप phase space में you imagine that something is going round and आप एक light उसके ऊपर shine करते हैं, you know the stroboscopic lights जो dance floors वगैरह पे films में होती हैं. So if that is shown, the light is shown with the same periodicity as the particle going round. So every time the light would shine, you would find the particle at one point. अगर आप frequency double कर देंगी light की तो आपको दो जगह particle नजर आएगा and so on. So this again is a useful concept and we use this later on because it reduces the dimensionality of things. I mean, from two, you can start looking at things in one dimension that you're only looking at specific time periods. This चीज को आप देख रहे हैं. So this is something we are going to use. So there is a linear stability analysis which is done. For example, you have these two Q dot and P dot, two coupled first order differential equations. And the first thing that we try to look for are fixed. So these are those points in state space or phase space where all time derivatives are state variables are zero. And so you can calculate then like looking at differential equations. This is a simple system case में सिर्फ दो equations है, but in principle you can be looking at more equations depending कि आपकी original equation कितनी उसको आपने कितनी autonomous equations में divide की. So fixed points tell us if you do a little perturbation whether a point is going to move towards the fixed point or away from the fixed point. And then people typically use this Jacobian matrix, and then you can write down a determinant where I is a unity matrix, and f df1 over dq is, let's say, f11, df1 over dp is f12, and so on. तो आप ये characteristic value lambda की determine कर सकते हैं. So and from this, then this lambda gives us some idea about the way the trajectory is behaving. Either it is attractive or it is repelling. So हम कभी attractive का लफ्ज़ इस्तेमाल करते हैं, कभी node का करते हैं. And then it may be ये तो sand node लिखा हुआ है. It may be moving towards a fixed point from one direction, but moving away in the other direction. So that becomes like a saddle point. एक तरफ से you have a minimum, and then on the other side, जैसे घोड़े की काठी होती है, you have a maximum on the other side. So these are all things that we use when we do our dynamical analysis. And okay. Acha. Now, most problems related to linear theory are now not so interesting. People have done a lot of the stuff. So पिछले 2-3 decades से non-linear problems have become very important, that we try to look at differential equations or evolution equations which are non-linear in nature. So about 20-30 years ago, in the 1840s, there was a Scottish engineer canal engineer by the name of John Scott Russell. ये आपको हर Soliton के text में, किताब में, you will find this story over there, that he was riding along a canal, and there was a boat in the canal which was, उनकी canals इतनी चौड़ी नहीं होती जितनी हमारी है, because they are smaller. So that boat was being tugged along, pulled by 2 horses. So John Scott Russell was moving with the boat. And then he saw that boat ke aage, at the prowess of the boat, a hump had formed, a hump of water. And he sort of got curious about it, and he started observing it. And then what he saw was that the boat stopped, it reached its destination, but that hump which had formed, that continued to travel for many, many miles. And John Scott Russell was fascinated by this, कि ये किस तरह से ये एक hump जो है, ये travel कर रहा है. So that was a solitary wave. अच्छा, 50 years later, I think almost during the end of the 19th century, two Dutch mathematicians, Korteweg and De Vries, these are two people, Dutch mathematicians, they tried to model this type of a wave in a shallow water channel. So they wrote down the mathematics. So they came up with this equation, the equation A, which is a nonlinear evolution equation. It's a partial differential equation, and with time and one space variable. Okay. So this is a nonlinear differential equation because phi jo hai, that is occurring. If you look at the second term, I can put the phi inside and it will become phi squared. So that makes it a nonlinear equation. D3 over d psi cube will give me the order of the differential equation. So it's a third order partial differential equation with a quadratic nonlinearity. फिर बहुत सी equations develop हुई with different orders of nonlinearity in more than one spatial dimension and so on. But this is the kind of fundamental equation which was developed. And then it was seen that if you go to a co-moving frame of reference, you can reduce the order of this equation and it has an exact solution given by D. And that, if you see the graph on the right-hand side, that is the hump which was observed by Korteweg and De Vries, this bell-shaped structure. So why people got very excited with this was कि ये एक non-linear differential equation है जिसकी एक exact solution model है. Normally, we have methods, generalized methods for solving linear differential equations, but not for non-linear partial differential. So हुआ काम खत्म हो गई बात. Then in the late 50s, early 60s, when computers started coming up, there were two scientists who did a computer modeling of this. That was, they were Zabusky and Kruskal. And when they did the computer modeling, they saw these type of structures emerge. And then they saw also that in the numerical simulations, if two of these structures collide, so they behave like a perfectly elastic collision. So they then gave this solitary hump the name of a soliton. आपको पता है particles को on या TON की ending के साथ वो चलते हैं, like electron, proton, वगैरह वगैरह, and so on. So this became known as a soliton. And so these have been very well investigated in not only plasma physics, but in fluid mechanics, fluid dynamics, and many other parts of physics, and even economics में भी लोग ये equations अपनी जो mathematical करते हैं उनको इस type की form में लाने की कोशिश करते हैं.
So can I ask a question here? So basically, what you're saying is if you have a soliton coming in like this and another one of equal energy coming in like this, they would just collide and then
go back. That is what the computer simulation.
That's what the simulation showed.
Yeah,
okay.
And this has been confirmed and reconfirmed many times. Even I think Arush has done some work which has been related to these. So this is a one soliton solution. So you can write a multi-soliton solution, which is more complicated. And then certain methods also developed over time where you could do a sort of a Fourier transformation for nonlinear equations, but that is called the inverse scattering techniques, which is doing it in a very. And other methods developed. इन्होंने जो काम किया that was with the Hirota method. So certain class of equations can be, for those you can write down multi-soliton solutions. And then if you look at the solution, what is interesting is the amplitude of the soliton can be expressed in terms of this velocity. And the inverse width of the soliton is also dependent on the velocity. So the faster the amplitude, the faster the soliton, उसका amplitude भी बड़ा होगा. मगर उसकी width जो है वो कम होती जाएगी. So it becomes taller. So if there are a number of solitons, they will order themselves. The faster ones will move faster, they will be higher, they will be thinner. And as you come down, the solitons become fatter and lazy, and they have smaller amplitudes. So, so people have been investigating this, and similar equations have come up. And it's not always possible to write down an exact solution, so people use other methods also. So one of the methods that is used is, again, trying to write down this KdV equation as a pair of first-order autonomous differential equations. So you can investigate them, look at, attracting points, whether it'll form a center or whether it will form a saddle node. So I don't want to go into much detail over here. But then if you were to do a phase space analysis of this, and it's nonlinear differential equations expressed in two equations over here, two first order equations. तो अगर आप इसको देखें तो जो आपको blue curve नजर आ रहा है, that corresponds to a solitary profile. अगर हम उसकी time series plot करें तो then you get the soliton back. और जो अंदर है इसके, those would be like non-linear periodic waves. So that is the one given in red. Zishan does all the numerical work, so I'm not really an expert on the computer. And so this is a powerful tool that we now have with the computer at our, which is available to us. अगर एक solution जो मिलती जुलती है इस तरह की equation से, maybe it has some different non-linearity or whatever, if you can't write down an exact solution, you can do this type of an analysis and say that you have a solitron or a solitary wave. So ये जो मैंने बात की थी कि अगर आप इस KdV equation के conservation laws देखें, so there are infinite number of conservation laws. You can keep taking moments of this equation with phi and integrating it. And if you can express that thing in terms of a continuity equation, then you know you have a conservation laws. It's a very tedious process. एक दो करने तो आसान है, but people have now concluded कि वो it's literally infinite. So that also
can one get some kind of a Lagrangian for to derive this kind of equation?
मैंने इस तरह से तो नहीं देखा है, but
energy solitons होते हैं.
Energy, हाँ, you can, I suppose, but they take moments in a very sort of आप इस equation को you write it as d over dt and then that's a d over dx and something inside. So that begins to look like it. Then you take a moment and do it again. Then you take another moment and do it again. वो हर step मुश्किल होता जाता है because it's not that simple. But I don't do the Lagrangian formalism, so I have not seen कि ये इसकी जो robustness है, whether it has been tested in the other way or not. So anyway, so बहुत सी फिर equations were developed which have solitary solutions or solitons. They exhibit solitons. One other equation that came up was the shockwave solution. Shockwave equation. ये आप देखें कि इस equation में और the equation that I showed you before, इस term का फर्क है. This we had a third order derivative over it. This is a second order derivative. This is due to dissipation. And again, you can go to a co-moving frame and write down its exact solution. So अगर मैं इसको plot करूं तो it looks like that. So although shock waves were known before, but this Berger's equation, as it is called, gave us a way of exactly looking at a shock wave in terms of an exact solution. So इसका भी हम उसी तरह का एनालिसिस कर सकते हैं. ये जो हमने एनालिसिस किया इस टाइप के ऑर्बिट को हम कहेंगे the blue one, that this is a homoclinic orbit. It has one center and one saddle point. F1 is the saddle point and F0 is the center. Okay. So when people looked at a shock wave, and then they did a similar nonlinear analysis. So they came up with an orbit like this. उसी तरह हमने equation को दो first order autonomous equations में divide कर लिया. And then you have this, if you look at the green curve outside वाला जो है, so it has two saddle points. It's like this. ठीक है? So this is, if you plot out this in terms of the time series, you get the shock wave. वो front आपको नजर आता है. So you can calculate all type of things, the thickness of the shock, the speed of the shock, and so on. और अंदर जो है, those are non-linear periodic type of waves which are going on. You know, the orbits inside the this. और इसके बाहर then you're not interested in looking at that. So there are two saddle points over here and one center. That is the way the equation works out. So, okay, now then people have done this type of an equation, which we've also looked at, that this is a mixed equation. It has the third order derivative and the second order derivative. So this is called the KdV equation, the Korteweg-de-Vries-Burgess equation. So this is more difficult to look at. इसकी exact solution भी देखना जरा मुश्किल है. But if you do a dynamical analysis, then again you see आपका it is reflected in these base plots also. And then when you see the time series, you see कि उसका एक oscillatory part भी है, and there is a shock-like part also, and the solitary-like part also, which is there. So these are all very standard, well-known equations and the methods to look at them. So literally thousands of papers have been written on the KdV equation and the Burgess equation. So what we started looking at many years ago was something which is known as adiabatic trapping. And this is, you have particles which are distributed, but some particles get trapped in a potential. And so there were two ways people looked at it. It was started in 1957 with the work of Bernstein, Green, and Kruskal. So उन्होंने at a macroscopic level इसको देखा कि trapping हुई, how it has affected the distribution function. Then there was another approach which was developed 10 years later by Gurevich. And so this was at a microscopic level. So you start with your distribution function. If there is some potential present, which may be due to a heavier charged particle, so the electrons will get trapped in it, or they will get reflected from it. And when they looked at that, so, and if the field is slowly varying, so then you can say okay, it is almost constant. So that is why we talk about adiabatically getting trapped. So without going into too much of the maths, what finally came out was कि जहाँ आपकी trapping हो रही है, let's say if you look at the lower diagram, so at that point your kinetic and potential energies are equal. So that becomes the kind of a trapping condition which is made over here. So if you went through the maths, you did your Maxwellian distribution function, and you did all your integrations, etc. You saw कि आपकी जो अगर मेरे पास trapping ना होती, I would have had a Boltzmannian distribution for the, let's say, the electrons. So it would be exponential raised to the power of E phi over T. तो अगर मैं E phi over T को छोटी quantity consider करूं, because T is a background quantity and phi is some type of a fluctuating potential, you can say. तो अब मैं इसको expand करता हूं, तो I will get terms like 1 plus phi squared plus phi cube and so on. When we did this type of trapping, it was seen by Gurevich long time ago. For a shallow potential case, you get 1 plus phi 3 by 2 over term. So your first nonlinearity becomes a fractional nonlinearity. Then you have your phi squared term, then you have a phi 5 by 2 term. तो हम बहुत ज़्यादा nonlinearities नहीं consider कर सकते. So we stop at the phi 3 by 2 nonlinearity because it is stronger than the phi square nonlinearity because E phi over T is a small term. Okay, So when we had a Georgian professor working in government college for about 5 years, Professor Sinsadze. He's now passed away. He was a very clever man. So he got us started on to looking at these type of nonlinearities for a quantum plasma or a degenerate plasma. So ये मेरी Fermi-Dirac distribution है. I have a potential entering the distribution function energy में kinetic energy भी है, potential energy भी है, और mu जो है that is the chemical potential. So ये when we tried to integrate this, we made use of the various things that you do, change of variables, etc. You use the Fermi integral method कि कहीं आप limit में आप infinity लगा देते हैं, if it's a large quantity, मगर अंदर आप उसको retain कर लेते हैं. These are things that probably people study in their statistical physics when they do quantum statistics. So when we did all this, so we saw कि जो हमारी let's say number density हम कैसे calculate करते हैं, that you integrate over the distribution function and then you're left with the number of particles या number density. So we had a strange nonlinearity which came up, which was not 1 plus another term, phi raised to the power 3 by 2, but 1 plus phi, the whole thing raised to power 3 by 2. So we said, okay, we'll try to solve these problems without, expanding this. So we left it like this. And then you have the temperature term. Temperature is small. So this is a temperature correction term, but this is the number density that you would get for a partially degenerate plasma. If you forget about phi, आप probably अपनी statistical physics में ये पढ़ते हैं कि Ne is going to be n naught plus into 1 plus t squared. तो अब बीच पे चूंकि एक trapping potential मौजूद है, so that trapping potential is occurring, but where it's not just the simple term with a different power, but 1 plus something raised to a different power. So if you have a plasma which we have considered कि उसमें electrons भी हैं, positrons भी हैं, और ions भी हैं, quasi neutrality is maintained. Ne is equal to Ni plus Np, the number density of the three species. So positrons में वो sign change आ जाता है, and then of course ratios आपको रखने पड़ते हैं, and that is expressed through that beta. Your charge neutrality is present. You can't take electrons and positrons being equal because we have an ion component. So we've been dealing with this type of nonlinearity for quite some time now, and so we've done different problems over the years. So इसमें we've looked at a three-component inhomogeneous quantum plasma, which means that the plasma is not uniform. It may be more dense here and less dense far away from the center. So that the inhomogeneity will cause particles to drift, because plasma may, when you have your pressure term, and if that del P, agar aap equation of motion dekhe, that is perpendicular to B, then the particles will drift with some drift velocity, which is typically going to be B cross del P. So particles are subject to all types of drifts in a plasma. So this particular drift is called diamagnetic drift, because mostly all other drifts are single particle drifts. So this is a fluid drift. इसमें सब कुछ participate कर.
3 components कौन से हैं? So 3 components.
Electrons, positrons, and ions.
And what's the environment?
It's could be a neutron star or some exotic plasma like that of a dense astrophysical object. I think we've used
Neutron
numbers.
Stars probably will not have.
Well, they do have positrons. They have electrons and ions, and positrons are produced.
Don't they just
maybe,
capture them all and?
Well, it depends on the time scale you're looking at.
Right.
If it is a short enough time scale, you feel the protons till they annihilate themselves. So this is the geometry of the things that we are looking at. And there is a density inhomogeneity given by del and naught. And we are looking at a wave which is electrostatic. And most of the wave is propagating along the magnetic field. And there is no B1. There is no fluctuating wave ke saath associated magnetic field. That is why we call it an electrostatic wave. So these are, for example, a very well-known wave is the ion acoustic wave, where if you're looking along the magnetic field propagation, then you don't feel the effect of the magnetic, because there is no Lorentz force acting over it. So we look at small angles of propagation here, and there's a density, so there is a drift. And now, as I said in the beginning, that these ions are much heavier than the electrons, as you know, तकरीबन 1800 गुना weight ज़्यादा होता है. So we can consider the ions to be classical and the electrons to be degenerate. They are, they follow the Fermi-Dirac distribution. But ions ke liye we can write down a simple fluid equation. Now this is the generalization of the Navier-Stokes equation. अगर Navier-Stokes होता fluid होता तो ये electromagnetic force ना होती, इसकी जगह कोई हमारे पास pressure gradient होता या कोई viscosity term होती, whatever is there in fluid mechanics. And here we've looked at some ion neutral collisions because neutrals are always present. And so these ions are considered to be cold with respect to the electrons. So we can neglect the pressure term over here. यहाँ पर grad P वाली term कोई नहीं है in this equation. And then you have your continuity equations. Since we are looking at electrostatic waves, we have a Poisson equation. And so if we go back to the expressions that we had developed for the electrons and positrons, when we reach our Poisson equation, so we will use these are the number densities which we will use for the positrons and the electrons. And then there is a special method which is called the drift wave approximation in plasma physics. It's very widely used, and you look at low frequency waves. By low frequency, we mean lower than the ion gyro frequency, ion cyclotron frequency. अगर आप उस range में waves को देख रहे हैं, so you can approximate your perpendicular motion of your through these drifts which are taking place. I'm not deriving all this, but the first is what is known as the E cross B drift, then you have a collisional drift, and then you have a polarization drift. That is the last term, which is also known as a startup drift. जब आप switch on करते हैं system, तो it changes, the field changes with time and the particles move. अगर वो steady है उसके बाद तो they stop moving. So इसको polarization drift कहते हैं. And this affects the ions more than the electrons. And so we use this drift wave approximation in our equation of motion. कि जब हम इसको solve करते हैं तो हम ये जो convective derivative वाली term है, vi dot del vi, this is a non-linear term. तो इसमें हम vi की जगह we can use v per I over here. So that is the drift wave approximation. कि ये एक किस्म की background drift है जो plasma में मौजूद है. It's not totally background because इसमें electrostatic potential वगैरह E can be represented through del of I, the electrostatic. So then you put all this business into these equations and do a lot of algebra, and which I'm not going to pull you with. So we, in the end, get an evolution equation which looks like this. So we have this first term, which is our evolution term, और उसमें जो पहली term में जो second beta वाली term है, that is the positron contribution. Then you have your temperature correction term, and then the other terms that are occurring, which are non-linear terms. So ये बाकी ये lambda Fe is the Fermi Debye length, which is basically a screening length, which plays an important role in plasma physics. तो अब ये non-linear equation है, इसका कोई solution नहीं, ठीक है? There is no exact solution to it. So we have to look at one of the more approximate methods. And if you look at the first term on the second last line, that is going to be like a third order derivative. So isko hum kehte hain, this is the dispersive term. So if you go back to the KdV equation, you had d3 phi over d phi cubed x cubed. So that is the dispersion. अगर मेरे पास, for example, light wave है, तो light wave की dispersion relation is omega is equal to ck. This is a non-dispersive wave. मगर अगर किसी वजह से कोई medium ऐसा है कि you get some term like ck, omega is equal to ck plus some term which is, let's say, proportional to k cube. So that will be your dispersive term. Then your phase velocity and group velocity are not the same. और उसको हम dispersion कहते हैं, जिसकी वजह से आपका medium के through जब light जाती है, तो it tends to either bend this way or that way, depending on your.
The term fourth order length is also this d by dt outside.
Yes, it is. It will to d by dt and then d squared. Now, once we go to a co-moving frame, तो हम देखेंगे कि इसका structure जो है वो मिलता जुलता है. और जो दूसरी term है in the second last line, इसको आप fourth order कह रहे हैं.
इस वाली term को.
तो it's a cubic.
एक बाहर भी d by dt.
एक बाहर है और अंदर second order है.
एक बाहर d by dt है, एक ये d by dt है, और d2 by dy.
वो that बाहर वाला will get.
You will integrate it out somewhere?
We will integrate it out. It will get integrated out when we go to a co-moving frame. So this is your dispersive term. And the second term on the second last line is like your viscosity term. So this is like a KdVB equation. कि इसमें dispersion भी है और dissipation भी है. But now non-linearity is a fairly complicated business. कि इसमें दो terms आ रही हैं, एक phi वाली और एक beta phi वाली, and with a fractional power. So these are all these different things that symbols that we have used. And if you go to a co-moving frame of reference, you can integrate it out. If you integrate this equation 10, and then you can look at, if you drop the dissipation term, you have a Berger-like equation जो integrate एक दफा और हो जाती है, and you're left with an expression like this. And this is the I1 and I2 are the integration constants. It depends कि आप उसको कैसे देख रहे हैं. One can say that at infinity, on one side it will go to some finite value, on the other side it may go to 0, and so on. That those boundary conditions are chosen according to the problem that you are looking at. And then if you deal with this equation, which is not easier to deal with, so we have divided it up into these two autonomous equations. और चूंकि हम इसकी exact solution नहीं लिख सकते, we've looked at these this thing in phase space. We've calculated the fixed points. We've seen कि उसका orbit किस तरह का है, and we see that this has, we get a structure like this. So ये जो blue line है, we see that it has, there are two structures over here. There are two shock waves over here. इससे वो इधर क्रॉस नहीं करेगी because of the way 1 minus phi r है raised to the power of 3 by 2. So अगर हम सिर्फ एक एंड से देखें तो you have
कर्सर यूज कर सकते हैं.
ये जो है हमारा saddle point at F2 and F3. This is for one shock wave. अगर आप दूसरी रेंज में देखें तो then you have F3 और F4 पर आपके channel points and 2 centers at F naught. So if I was to, which Zishan has done, and I'll just show you. So parameters are पूछ रहे थे, these are the typical parameters that we use.
White dwarf.
White dwarf के हैं ये B naught is very strong magnetic field. In fact, we've done some work where quantization has also been taken into account into these equations, that the orbit of the electrons gets quantized. And number densities are very high, which are degenerate, and so on. So अगर मैं इसकी time series plot करूँ, तो I get shocks. So I can get shocks or under what looks pretty periodic, but it is not really. These are the nonlinear periodic waves, which are the inner orbit. So the things on the red line. So there are lots of these nested things inside, depending where you start off from. And so similarly, we've looked at the way these profiles move, change with different number densities, different angles of propagation, वगैरह वगैरह. So, and then similarly, अगर उस equation में जो हमारी main equation थी, ये वाली जो आप कह रहे थे कि fourth order equation है, if you drop the dissipation term, then you're left with the dispersive term only. So this is like a KdV-like equation. और इसको भी we can integrate it once when we go to a co-moving frame of reference. In fact, it gets integrated twice. And just note this, that this is now, we've reduced it by going to a co-moving frame and by using that boundary conditions that at infinity, all the perturbations are going to die out. So it means that I have an equation which goes like d2 phi over d psi squared equal to a lot of terms. Okay? Now, people have drawn this analogy that this is like a particle in a potential well, where you have m d2x over dt squared is equal to minus dv, some potential well over dx. So, iska structure वैसा ही है. So, so this we can say we can look at it as if there was a particle in a potential well, analogous. So this Saddev, he introduced this kind of pseudo potential, which has become known as the Saddev potential. And so when you don't have a solution and you can't write down that beautiful secant hyperbolic solution, so either you do this type of a Saddev potential analysis, and you know what the Saddev potential should look like for a solitary wave, or you do your dynamical analysis कि वो phase space में वो किस तरह के plots आएंगे उसके. So we see we do this, we can write down an expression for the Saddev potential and then plot out V versus phi. And these are the Saddev potentials for different values, and it has one maximum, one minimum, and it touches the x-axis. So this is V minus phi. V is on the y-axis and phi is on the x-axis. So अगर मैं इसको numerically भी invert करके बनाऊं, so I will get a solitary, different humps. So, and then if I put everything together, and I do a phase, the dissipation term and the dispersive term, so I will get these type of curves जो मैंने आपको पहले भी शुरू में भी दिखाए थे. This is like, it has some oscillatory part, it has a steepening. So what is really happening is that when you look at a wave, let's say a water wave at the समंदर के साहिल पे, तो जो बड़ी waves हैं, they come in, उनका amplitude बढ़ता है, and then they overturn and they crash. So if the overturning is stopped, in one case you will have a dispersive effect, dispersion की वजह से, and that structure will travel along in a stable fashion. In the other case, when it is beginning to overturn, वो steepen होती है, overturn होना होता है, so then some other effect like dissipation balances it out, and what you get is like a shock wave travel. ये जब पटाखा चलता है या बम चलता है, it is a shock wave which is traveling, and that shock wave hits you like this, and that is what creates the thunder or the noise जब जहाज चलता है. So similar things happen. So this is a mixture of this. So I think I won't take long. For example, I take this equation जो पहले हमने ली थी, and I've added a term over here, this last term, that this equation has some external perturbation. Okay, we have this equation, and then there is something which is disturbing this equation. There's some, I can use the different models for it. This is like a sinusoidal type of a disturbance. Something is hitting it, like as if you have a pendulum, वो अच्छी तरह से चल रहा है, and then you start slapping it with something periodically, तो उसका motion जो है, that will no longer remain predictable. So when we model chaos for these type of problems, we sort of almost put in by hand that there is some low frequency force which is acting on this system. And then when you look at this, so then you get these fancy graphs which you can Zishan ने workout किया है कि ये जो blue वाले plots हैं, that is the Poincaré plots, and that red वाले जो हैं, these are lots of lines which are, in phase space, and the Poincaré plots, things in blue, these curves which are over here superimposed onto these tori that I'm getting over here. This tells me that this system is periodic, because quasi-periodic, because वो एक ही लाइन में वो Poincaré points जो हैं वो आ रहे हैं. So eventually that whole line is filled up. If I keep flashing the light, तो वो थोड़े फर्क के साथ those points will be spread out. Or you can also do a fast Fourier transform, and then you will see कि certain frequencies के पास वो single points नहीं है, but there is some spectrum which is there. And so if you change your parameters, so you get your Poincaré plots start to, this is mode locking, where the external frequency and the natural frequency of the system, they lock up with one another, और आपके जो fast Fourier transforms हैं, they are already being spread out. So the system is beginning to look chaotic. So यहाँ पर वो chaos जो है वो ज़्यादा वाज़ेह है. Chaos means that it's not predictable anymore. You can't really say where these points are going to fall. Poincaré point अगला वाला कहाँ पर आना है, phase space में कहाँ पर जाएगा. So these things are known as attractors. Whereas it may remain confined within a certain space, in phase space, but you don't really know where that point is going to be. So that is what makes it unpredictable and chaotic. To take a simple example from everyday life, we look at weather and we look at climate. So these are things happening on different scales with all my instruments. And using classical methods, the systems are deterministic. But I cannot predict कि lumps के बाहर अगले साल 12 सितंबर को कितना टेम्परेचर हो. But I can say कि वो लगभग 25 और 40 के दरमियान हो. It will not be snowing. It will not be 60 degrees centigrade. But within that, I cannot predict exactly what is going to happen. Linear theory में या Newtonian physics में, you could exactly predict what it would be like 10 years later or 1 year later or 2 days later. When these non-linearities are brought into play, a deterministic system under certain conditions start displaying chaotic behavior. But then we can also say that there is some type of order in chaos. कि वो एक basin of attraction में वो रहेगा point, उसके बाहर उसके जाने के chances नहीं. And these type of diagrams, they have become known as strange attractors, because they have a strange shape. You can't predict the point kahan par hoga. So, and then again, if you look at your ये जो blue वाली lines हैं, your fast Fourier transforms, Now the frequencies are also all spread out. There are no sharp peaks. Natural frequency के साथ चीजें उस तरह से resonate नहीं कर रही. So this is a double well chaos, and this you can see are the Poincare sections, these dots in blue. So I think I should stop.
This is good. Thank you. Okay.
So I don't know how much sense was made to the students who don't study. I don't know whether you do nonlinear dynamics over here in your courses or plasma physics. So
It's not core. It's not core, but some people have explored. Yeah. All right. So thank you very much. So
thank you for having me.
Of other things, I now understand why there is a thing called blood plasma.
Hanji. Although it is not a charged particles, yes, plasma.
But now I understand why they call it a plasma.
Why they call it? Because it's
the jelly-like thing. Right. So, questions. मैंने तो ढेर सारे पहले पूछ लिए.
You are not allowed to ask questions.
Very reasonable. He can ask questions as a lump student.
Yes. So you have included your dissipative effect as an ion neutral collision in your equation of motion. जब मैंने ये काम किया था तो I ended up obtaining a damped soliton rather than a solitary shock wave. Is this because you used a E cross B drift approximation in it, or is something else going on?
No, I think it is this. I mean, this behaves more like a dissipative term rather than a simple collisional term. The way the equation is structured, and this, of course, कि आप एक drift wave approximation इस्तेमाल कर रहे हैं तो उसके साथ उसका structure उस तरह का आ जाता है.
जो मैंने किया तो बेहतर था या ये वाला बेहतर?
They're different. Yeah, you got an exact solution
yes,
out to the damped term, but it was not. You could call it a solitary wave, but not a solid, because yes, उसके उस तरह के robust laws नहीं होंगे. But देखने में वो soliton.
Yes, but the good thing was you didn't have to add an external periodic perturbation to see whether this is chaotic or not.
So I have a question that the two of the shock waves you showed, like one of them was like it was damping out, and one of them was growing.
They're both, it's a shock front which is propagated. So upar or niche are, it's leveling off somewhere. It's the thappad which is traveling. And वो उसकी angle पर भी depend करता है, उसको thickness आप measure कर सकते हैं, how fast it's growing, etc.
एक चीज अगर आप थोड़ी सी एक्सप्लेन कर दें, that will be more interesting. अगर butterfly effect or sensitive initial conditions, तो that will.
These are all. It goes into the definitions of chaos. It is extremely sensitive to initial conditions when you look at chaotic systems. तो ये शुरू का meteorology से हुआ था. There was a professor at MIT by the name of Lawrence. Not the Lawrence जो आप electrodynamics में पढ़ते हैं, but his namesake, probably 80 years later. He was, तब नए नए computer आए थे, and these mainframe computers used to take up a lot of space. They were big halls जिनमें मिला. So he was looking at weather and the variations which are being recorded all the time. And he, went out for his cup of coffee and came back and started looking at things again. And then he tried to compare कि जब system को वो start करता था, very near the point from where he had originally set the system, so there would be a divergence in the results. So small initial results, initial differences gave rise to big differences later on. And then he wrote down his famous Lorentz equation, which was a way of modeling this climate or these weather patterns. So they were very simplified. I mean, वो actual model जो था, वो उसका reality के साथ कोई उस तरह से directly ताल्लुक नहीं था, because that is what a model is supposed to do, that it gives you some essentials of what is happening. And then he saw कि ये जब attractors बनाए, so they were like in the shape of a butterfly flapping its wings, So that gave rise to this term that this is the butterfly effect. And then this whole thing came up that if a butterfly flaps its wings in Los Angeles, it can cause a storm in Beijing because it was totally chaotic within that phase space. So that is a phase space diagram. So दो चीजें हुई chaos theory में. One was this Lorentz model, which was a set of 3 first-order autonomous equations which modeled temperature changes and
Pressure.
Density or whatever. And so these were like, it was like a 3-dimensional system, and it was seen to go chaotic. So this was one early work on chaos, which is considered to be very fundamental. The other is the population model, which was in fact developed by a biologist by the name of Robert May. And he looked at a simple population model, but equation discrete. X n plus 1 is equal to, let's say, some constant a xn. तो अगर पिछले साल की आपको पॉपुलेशन पता है तो आप इसके हाल की कर सकते हैं, मगर a अगर पॉजिटिव है तो पॉपुलेशन वुड स्टार्ट ग्रोइंग infinitely. अगर a नेगेटिव है तो it would die out soon. So then he added like a nonlinear term axn into 1 minus xn. So then he saw how this system would behave, the discrete system. Now, so you can do it literally by hand when I do my class lectures. So we take out our phones and we calculate कि इस initial conditions से शुरू करेंगे तो क्या होगा, a की क्या value होगी तो किस तरह से behave करेगा. And then you can say at certain values of a, if my curve is going like this, I will reach a point where वो 2 branches बन जाए. फिर a की value आप थोड़ी सी change करें, 2 और बन जाए, फिर 2 और बन जाए. So आप देखते जाते हैं, and then eventually it becomes chaotic. So that is known as, we had done a bifurcation analysis over here also, but I thought that would be too much to show. So that is the period doubling route to chaos. कि जब वो bifurcate करता है तो हम कहते हैं period double हो गया. Then it period doubles again and again and again and again until it becomes, you can't see any pattern anymore. And so, this is the period doubling route to chaos, and the other is the Lorentz way of getting into chaos, that you look at differential equations. And you need a minimum of 3 differential equations to look at chaos. हमने वो third equation अलग से नहीं लिखी, हमने वो plug in कर दी है into one of the equations by adding that f naught cos omega t type of term. उसको भी एक third equation के तौर पे भी लिखा जा सकता है. But you need a minimum. There are many things which have been done. It's a very interesting field, and now there are a lot of good textbooks to guide you through this. क्या है? Strogatsky है किताब और बहुत सी है. And so you, and I think in all branches of, or in many branches of physics, it is the nonlinear problems which are important now, and because those are the ones that linear theory is very idealized. आपने छोटी सी perturbation ली, आपके पास बड़ी neat सी equation आ गई, आपने plane wave solution डाली, अगर आप waves देख रहे हैं, you get some solution. But so many people are doing this type of work, not only in plasma physics and mathematics.
Like all good things, your talk must also come to an end.
Yeah, I don't know if it's good. It's probably a good thing. So
then let's thank the speaker.
Thank you.
We can head over to tea and some fruit, and then you can continue with questions there.
Yeah, sure.
Okay. Thank you.
Thank you very much.
I think this is yours.
This is sorry for Sabi. You have to